my desktop. Yeah, double check. Okay, welcome back everybody. Today's Thursday, and then next week will be the last week of the summer. Okay, of course you know that. So we are continuously talking about shear and moment diagram. Now, do you remember in last class? We looked at shear and moment diagram developed on a simple beam just like this. This is the simply supported beam. Oftentimes people call this simply supported beam. This is very typical configuration. Pinned support at A, and then here roller support B. Three unknown reaction forces. You can, of course, determine those reaction forces by drawing free body diagram of the entire beam and then find out support reactions. Obviously. So in this case, AY and BY, those are the two support reactions. This actually acts as an externally applied shear force so that you create jump and jump, something like that at the end. So when we draw shear diagram starting from 0, this is a support reaction going up, jump, okay? How much? This much, same magnitude, jump. And then shear remains constant until you see the external shear loading P is applied. You have a jump down this much. Now all of a sudden internal shear is negative value, and then constant until you meet this support reaction By, in which this is, what's the value? Support reaction By is Pa over A plus B going up to 0. So start from 0, end at 0. This is the shear diagram. And after you complete shear diagram, based on that, you're going to construct the moment diagram. Starting from 0, shear is a constant value. That means the slope is constant, positive from here all the way to here. Now, all of a sudden here, shear becomes negative. That means the negative slope constant all the way back to 0. Okay? So obviously, you can construct this shear and moment diagram by using only that handout. So important thing is, please bring your handout with you and then take a look at it all the time, because that's the only information you can access. Okay? Now, this is the problem I purposely try to cut and cut two locations to find out the internal shear and moment as a function of x. And then we determine that shear is a constant value in this range. Shear is also a constant value for the rest of the range. So shear is constant and constant. It's not the function of x, it's constant. Okay? And that's one of the demonstrations that the equation actually supports this shear and moment diagram. And the moment looks like this is a linear function of x, positive slope. Here we go. This is, again, moment is a linear function of x, negative slope. This is the y crossing point, PA. So this is the line. So obviously, you can draw moment shear diagram based on the function of x you develop by cutting virtually for a given range. Of course, it's the same thing. Okay. I hope you understand the basic concept. Okay, that's quite important, because usually beam is not like this simple. Okay, you need to be prepared to be more complicated beams, and you are able to draw shear and moment diagram. Okay, that's the challenge. So today, let's just take a look at another simple configuration. This is a simple supported beam with a point moment applied. Go ahead. Question, Ryan.
Are you recording this right now?
I'm not sure. I am.
Okay.
Thank you very much. Yeah. Double checking. Yeah, you are recording. That's right. Okay. All right. So let's just take a look at. Am I sharing my desktop? Yes. Okay. Double checking. Okay. All right. This is another simple configuration. Simple supported beam. Okay. And then now this case, instead of point force, I'm applying point moment going clockwise direction. What happens? So what we did was the same thing, starting from the free body diagram of the entire beam. Try to find out the support reactions, and we did. The support reaction AY is negative M0 over L, so this is actually this way. Okay. So this is the direction of AY. Is a negative Y direction. Okay. By is m0 over L. Okay. And then, first of all, in the range from 0 to the half of L, I'm going to virtually cut at the location X. This is arbitrary location X. I just cut and introduce internal shear and internal moment. Try to apply summation of forces moment at point O. Determine internal shear and internal moment as a function of X. Then I realize the shear is, again, this is not the function of X. Shear is constant. Okay. This is a moment as a function of X. Oh, this is a linear function with a negative slope. I kind of know what kind of function should be. It's kind of similar to what we saw in the previous example, right? So let's just move on. So what is the next step here? What is the next step? I'm going to, of course, introduce another virtual cut. Okay. I'm going to introduce another virtual cut right here. So this is in the range from half L to L. Okay. So let me just draw once again a different range. So for the range for half L, actually, it's just more than half L, okay? Because this range includes the half L. So half L more than that, and L. So half L to L, that's the range. So that means, okay, I'm going to cut here. So this is once again the same support reaction, AY. This is support reaction M0 over L, negative X, negative Y direction. Okay. So now I'm going to introduce arbitrary distance X. Now X is in the range of half L to L. So that means, okay, so this is still X, but remember, this function is buried only this range. This is buried X range. And then this, whatever the equation you get out of this cut, you cannot apply in this range, invariant. Okay? Obviously. So X is always X, measured from point A to the right. But whatever the equation you get out of this cut, you cannot apply in this range. Of course, you already have those equations in this range. Okay, so once again, this is point O. You are going to introduce internal shear as a function of X. Internal moment, also function of X. Okay, then you're going to do the same thing. Let's do some of the forces in Y direction.
I have a question.
Go ahead.
So since we like cut over there, wouldn't we have a moment MO a part of our diagram?
If you actually use this segment, yes, you have to put equal and opposite moment this side, equal and opposite shear on this side.
Oh, I was talking about the moment on like the moment applied to the beam from like the beginning of the question.
Beginning of the question. Yes, great point. Yes, moment actually appears here, right here. So, great point. That's right. External moment MO, don't forget. That's right. Okay. It's a wonderful question, actually. I appreciate that. Okay, summation of the force in Y direction, Z equal to 0, okay? So this is negative M0 over L. Go ahead.
Doesn't that mean it has to be L2 less than or equal than X for the range? Otherwise, it wouldn't include that point moment.
Yeah, point moment is appearing at the half-L point. So question is, right here at this point, you can take either way. This is the location where internal moment shear dramatically change. So including this or including not this one is both correct. I guess it's your decision to. So you're saying this range set.
Because the other one doesn't.
The other one, the other one is kind of wrong too. Let me just fix it. So the other one, I'm going to probably not gonna include. Well, you can do this if you want to. So that means, okay, for the range from 0 to half L, I purposely ignored this effective moment M0. Then in the range of half L, you all of a sudden introduce M0 because this is going to change dramatically the shear moment situation internally. So this is the kind of critical point, sort of, I can say. Okay. So let's just do that. This seems to be better. Okay. Yeah, I agree. I kind of have a tend to agree for your point. Okay, that's right. When you draw shear and moment diagram, you kind of know better of what we are talking about because that's the location where we have a dramatic change. In other words, shear jump change, moment change happens also. Okay. So let's just move on. So this is summation of the force in y direction set equal to 0 minus m0 over L minus internal shear. This is a function of x set equal to 0. This is going to give you internal shear as a function of x. Okay. This is negative m0 over L. Then you realize, wait a minute. Isn't that the same? Oh yeah, it is the same. So this moment shear diagram, shear at least, it doesn't change at all. Shear is constant throughout the ranks. Shear never change. It's this value, always. That's one thing I know at this moment. Now, let's do a summation of the moment. And let's just take 0.0. Let's just set equal to 0. 0.0 is relocated right here. Now this is 0.0. Okay. So this actually gives you internal moment as a function of x. It's a positive moment. And what? Oh, this m0 over L also create positive moment. Oh, okay. So plus positive moment m0 over L multiplied by x, distance x. Okay, this is the x. And this m0 is actually negative m0. Okay, this is set equal to 0. This is going to give you internal moment as a function of x developed in this range of a beam minus m0 over Lx plus m0. This is kind of similar yet different function, isn't it? Those two are kind of similar to each other, yet different function. That means, wait a minute, so this is same slope, negative slope, but this is a y and x crossing point is different. Okay, so let's just draw a diagram here. Let me just zoom out a little bit. And I'm going to construct the diagram. Okay? And then first of all, shear diagram. This is x, this is a shear. And the other one is a moment diagram. Okay, so let's just make sure. So that's the location of the edge of the beam. And this is the location of where the moment is applied. Okay? Shear is easy. Right? Starting from here, M0 over L, this is a support reaction. So this is basically starting from 0. Support reaction is going to create the jump of this much shear. Okay? So the value here is negative M0 over L. Right here. And then it looks like all the way constant. Constant shear. And as you hit the location B, By is M0 over L. This is the jump. Going back to 0. This is the shear diagram. So inside of the beam, shear is all the way through constant, negative value M0 over L. This is shear. Internal shear is constant throughout this beam. Interesting. So if you know that much, you can say the slope of the moment diagram is the shear itself. That means, hey, all the way through negative slope. So first of all, starting from 0, right here, if you keep having negative slope all the way to here, what happens here? Well, of course, you're going to be negative slope, straight line, straight line, straight line, straight line, and hit here. Here is the location, half L, where you apply the external moment M0. Okay? Question, what is this value? What is this value? Area under the curve here. So this area. So this area is M0 over L times half of L. Isn't it? So what's this value? Yeah, M0 over 2 negative. That's right. Looks like this is the peak value of the moment. But what happens right here is you're going to apply external moment. If you apply external moment, what happens to the moment diagram? Jump. Okay. This is the positive direction, so jump up. Well, the moment jumps up. How much jump do you expect? M0. So this is a jumping up of a moment, M0.
How come it's positive?
It's a sign convention. If you take a look at diagram, shear moment diagram, sign convention, externally applied point moment is defined as positive clockwise. This is actually sign convention. So this is actually sort of, I don't know, it's like an agreement for everybody trying to draw a diagram. We have to come up with certain standard agreement. So this is sign convention. Okay. All right. So positive M0. So as a result, what is this value? Right here. Positive M0 over 2, right? Correct. And then shear doesn't change. That means the slope still remains the same. So what happens here is, again, constant slope, straight line, all the way to here, going back to 0. So this is moment diagram. Okay. So any question here? This is very simple drawing because it's a simple supported beam with very simple external loading, either point force or point moment. So you can draw it fairly simply. However, I can always create more complicated problem easily. That's the beauty of the shear moment diagram. And then as you start taking solid mechanics, you really show yourself mastery skill set before you actually start doing a real solution in solid mechanics. Real solution of solid mechanics involves, hey, this is the beam, we designed it, okay? This is a support, this is a loading, distributed, and blah, blah, blah. What is the maximum internal normal stress developed in this beam? First step is draw shear and moment diagram, determine the critical point. In this beam, what is the critical point? Obviously in the center. So obviously, right here, x equal to half L, you can take either moment becomes negative m0/2 or positive m0/2, either way. If you include x, this point, in other words, my definition of range. My definition of range is this. If so, what is the moment? Right here, moment is this value. But once you include the halfway point, all of a sudden, burn, you can take it, well, no, moment is plus m0/2. Well, no, moment is negative m0/2. Right here, x equal to half L, you have a dramatic change of moment internally. This is a critical point. You have to design very well your beam right here. So make sure your beam can take this much sudden change of moment internally. Is your cross section taking this much sudden change of moment? This is a critical location. If the earthquake hits, this is the location your beam fracture. Okay? So that's solid mechanics. In order to step into solid mechanics, you have to master this in this class. You can never survive in solid mechanics, guaranteed. Okay? Then solid mechanics, you're going to take it from here, then cut into the cross section. Okay, so what is the best design of cross section? Is this I-beam or simple supported this beam, hunk of metal? Or is it too heavy? Or maybe this beam or that beam? Or cross section, this beam? What is the best? That is solid mechanics. So what is the material? What is the length? What is the maximum loading you can take? That's solid mechanics. Go ahead. Question?
What if it has like a complex shape? I mean, that's probably going to be
complex shape means not the straight beam.
not a straight beam. Is it just different?
It usually doesn't give you much benefit. In other words, a complex beam need to come with certain purpose. The beam, as it is originally designed, it is usually designed to do certain things, typically like a hoist or something. You can move it around like this and hoist up heavy things. So complex shape may not consider it as a beam, but you can sometimes design such a thing. If so, you can still do this kind of thing. Internal loading analyzed, and then find out the critical location, cut into cross-section, pick up the material, design the cross-section shape, design the loading. Now at that point, you probably want to use the software. So you become a senior student, you're going to pick up the software, analyze structural behavior integrity, okay, internal loading, factor of safety, okay, stuff like that. I hope you can climb up to that level. Of course, you're paying a lot of money to climb up to that level. Don't waste your money, okay? Anyways, let's move on. Next page. This is homework. Homework. So now, as a homework, you have to deal with this distributed loading. You know, let's just start dealing with the simple thing. Uniform distributed loading. Suppose if you have a uniform distributed loading, what happens to your diagram? What is the impact of this uniform distributed loading? Anybody?
Simultaneous.
So this is a uniform distributed loading.
It's no longer constant.
So what's no longer constant? Shear?
Shear.
Shear is no longer constant. Okay. So how does the internal shear change with the distributed loading? Internal shear linearly change. So the magnitude of distributed loading is a slope of a changing shear internally. Okay, again, let's just take a look at the handout. Once you introduce the distributed loading, okay, this is going to be a slope of a shear diagram. So the shear is no longer be constant. Okay, so you have to deal with that. This is governed by two equations. This equation and that equation. Okay. So you have to handle that. And also, don't forget about externally applied moment here. this is clockwise, it's a positive moment applied. Okay? So I think the stepwise, you're going to, first of all, find the support reactions at pin A and then rotor B. Support reactions comes up AY and BY. And then you're going to draw shear moment diagram. Okay. Now, this is optional. If you want to cut a certain segment and find out the function shear and moment as a function of x, you can do that still. If you want to do that, that's fine. But with this handout, you can certainly draw shear and moment diagram just like this without take a look inside of the what is the function you're going to develop in this range and that range kind of thing. This is just a demonstration. Okay, I wanted to show you this is a mathematical function. If you cut into the beam, you can develop shear and moment internally developed as a function of x, right? That is going to essentially the same as this. In other words, of course, in this problem, you determine shear as a function of x. This is actually not the function of x. It's a constant, minus m0 over m. It's a constant. Okay? Mathematically speaking, it's a constant value. Now, how about this? Okay. Moment right here, mathematically speaking, as a function of x, this is minus m0 over L x, right? This moment is a function, this is minus m0 over Lx plus m0. So those are the mathematical functions representing those lines. Okay? So as you do your homework, it's your decision, but you can still, hey, I'm curious about, suppose if I cut here, what kind of internal moment shear you can develop as a function of x. You can do that. Suppose if I cut here, what kind of function can I get? And then based off of that information, you can do a shear moment diagram. Or you can take a look at the handout. And based off of the handout information, you can do a shear moment diagram. Either way. Okay. It is going to make you think a little. So please don't underestimate shear moment diagram. Okay. This is a homework. Next page. Let's take a look at another example. Here we go. So it's getting more complicated. This is simply supported beam, yet you have multiple point loading applied here, 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 here. Okay, so let's just take a look. Draw the shear and moment diagrams for the beam. It looks like 1, 2, 3, 4, 5, 6 point loading applied at various locations. It's an obnoxious problem. I don't like it, but you have to handle it. Okay. So first of all, let's draw entire free body diagram of this beam. Okay. So you have two, well, let's change the color here. Sorry, let me just change the color. This is the unknown support reactions, AX, AY. And of course, here's a BY. Now, yeah, okay, BY. So this is same as rotor, BY. Okay. Now, you have external loading, lots of it, quite frankly. This is 2 kilonewton, 2 kilonewton, 2 kilonewton, and 2 kilonewton. And here is 4 kilonewton and 4 kilonewton. 2 kilonewton multiplied by 4. This is 4 kilonewton multiplied by 2. So lots of external loading applied. That's how much you know. And first attempt is you try to find out support reactions. And then obviously, suppose if you do summation of the force in x direction set equal to 0, you can tell this is 0. Okay, so let's just do summation of the moment at location A. Let's just set equal to 0. This is going to eliminate AX, AY contribution to the moment. So this is going to give you By times 8 meters minus 4 times 7.8. Minus 4 times 0.75.
It's around 0.8, so it should be 7.
Yeah, that's right. So what? Wait. This is 8. Okay, so By times 8. Okay, so now what? Minus 4 times, I don't know what I'm doing here. Minus 4 times 7.25, that's right, 7.25. Measured from A, that's right. And another minus 4 times, this one is 6.25. Right? This is this 4 and that 4. And then bunch of 2 kilonewtons. 2 kilonewtons times this is 4.25 meters. And another 2 kilonewtons, 3.25 meters. Another 2.25 minus another 2 kilonewton, 1.25. Equal to 0. From here you can get By. So By support reaction is, I believe, 9.5 kilonewton. Is that correct? I hope. So this is one of the support reactions you can develop by taking the moment at point A. And summation of the force in y direction. You're going to set equal to 0. So this is going to be Ay in positive y direction minus 2 kilonewton, 4 of the forces. And 4 kilonewton, 2 of the forces. Plus By is 9.5 kilonewtons. So from here, Ay is equal to 6.5 kilonewton. That's what I got. Okay. All right. So now I'm trying to draw shear and moment diagram. Now I'm not going to cut because, you know, the problem is if I cut here, you can get one function of shear and moment. If you cut here, another function of shear and moment. If you cut here, another function of shear and moment. If you cut here, you're not going to do this. Right? You don't have time for that. Of course you can do it, but I don't want to do that. So anyway, so you're going to basically go back to, hey, this handout. By looking only at the handout, you're going to draw shear and moment. Do you have a handout, by the way? Please bring it with you. Okay, it's going to be your benefit. Okay, anyways. So I'm going to draw, first of all, shear. Okay, so I'm going to draw a shear diagram here. Really carefully. So All right, so let's just be careful about this. Is end point of the beam. This is the beginning of the beam. And then shear is given by kilonewton. X is meters. Comes with unit. Be careful about that. And shear starting from 0 as usual. Now right here you have a support reaction. AY comes in. AY is 6.5, so you have a certain jump up all the way to here. 6.5 jump up. Let me just zoom in a little bit. Okay. So you jump up to 6.5. Okay, so you have jump up 6.5 starting from 0. Now you have this is where point force 2 kilonewton applied. Okay, so you have a jump of shear. You jump it down to 4.5, isn't it? It's 4.5. And up until right here, shear is constant. Yeah. Right here, you have another 2 kilonewton jump. Okay. Then you jump down to 2.5. I think I made a mistake. Sorry. Let me just redraw it. I don't like this. Sorry. Need to be careful. That. Okay, so starting 0 all the way to 6.5. Next is 4.5. Yeah, right here. I write that 4.5. Then shear is constant up until you hit another 2 kilonewton force. And you got another jump. Jump down to 2.5. Is that right? And it is constant up until you hit here. Right? Then now you have another jump of 2. So now you hit, 0.5. Okay. And then shear is constant up until you hit another point force. Okay. So here's constant. You get another jump to here. Oh no, what's the value? So this is minus 1.5, isn't it? Minus 1.5. Okay. And shear is constant up until here. So here's constant negative 1.5 up until here. Then here's another jump, 4 kilonewton jump. So that is jump down fairly deep. Okay. So let me just temporarily erase this. Then, so this is minus 5.5. Okay. And it is going to be constant up until here. Constant. And here's another jump. My goodness. goodness. Okay. So this is minus 9.5. So I hope this can go back all the way back to 0 right here. Oh yes, By is 9.5 kilonewtons upon reaction, go all the way back to 0. This is shear diagram. Do you want to do moment diagram? You can do it, of course. So, of course, moment diagram typically requires shear diagram. So, after you know the details of shear, now you're ready to construct a moment diagram. Now, let me just zoom out. So, moment diagram requires the information shear diagram, obviously. So, this is X. This is moment. Now, moment comes with the unit kilonewton meter. Okay. Now, one thing we know, what do we know about the moment? What do we know about the moment? Starting from 0, yeah, that's one thing. And then also, what can you tell about the moment out of the shear diagram? In other words, the value here for this range, okay, for this range, what do you know about this range? Slope is 6.5. It's very, very steep slope, fairly, okay? So you are going to probably have linear line drawn straight. I just missed. Okay, sorry. So you're going to draw a linear line, fairly steep slope up to here. Slope is 6.5 for the lengths of, how much length? For the lengths of 1.25 meters. So this is 1.25 meter length, 6.5 kilonewton. What is the value right here? That's right. 6.5 times 1.25. It's like 8.125, correct. So now you know the magnitude here, and also slope. Slope is 6.5 kilonewton. Okay. Now, this slope actually changes for the next segment, correct? What is the slope now you change?
4.5.
That's right. So slope is kind of changed. Then you can tell this value, right? So 8.125 plus what? This area.
So that's just 8.125 plus 4.
Plus 4.5 times 1, yeah.
So that's 12.625.
12.625, correct. Now I think you're getting it. And then here, the slope is going to be changed right here. So the value here is, of course, 12.625 plus the area, this area, okay? So if you repeat the same thing, this is going to be 15.125. And then, once again, slope changes. The value here is 15.625. Now, you can tell right here, the shear gets 0, right? Shear gets 0 means slope 0. if you see the point of slope 0, that's the peak point. So this is where the maximum moment happens, because that's the location shear becomes 0. Okay, so this is a critical point. So when you design this beam, hey, this is a critical point. Okay, by drawing moment diagram, you know that kind of information. So now, right here, what happens? Now the shear is negative value. That means the slope becomes negative. So you begin to have this kind of slope. Okay, the value is 15.65 minus the area. Now you have value 12.65. Okay. Now what happens here? Well, the shear becomes negative, but larger negative. That means steeper negative slope. Okay. Actually, much steeper, sorry, I think. So this is much steeper slope. So right here is 12.65 minus, again, this area. This is going to be 7.125. And once again, the slope is steeper from here. Go all the way back to 0. This is the moment diagram. And then by drawing shear and moment diagram, important information you can discover is, hey, this is the maximum value of moment. Okay. This is a critical point when you design a beam. So, like I said, if you take solid mechanics, even before you actually doing analysis of solid mechanics, you have to draw shear and moment diagram, determine the critical point. If you cannot do this, that means you are not having the mastery skill of statics. You are not even qualified to do solid mechanics. So don't underestimate this shear and moment diagram. Professor teaching solid mechanics requires you to have this mastery skill. If you don't have it, okay, you're not even qualified to take solid mechanics. That's what I usually say at the very beginning of solid mechanics class, freaking students to death. Oh my goodness, I'm not qualified. Well, of course you're not qualified. Who the hell is your static teacher? That's my comment. Now I cannot say that because I'm the teacher. I'm sorry. So please master this thing. Anyways, so I guess bottom line is very simple. You have to simply follow the equation, which is very simple equation. 2 equations. Okay, relating external loading to internal shear, relationship between shear, internal shear to moment, and then if you integrate, of course, you're going to find out area under the curve to determine the jump. It's a very simple deal. So it's the governing equation. Okay. Any question here? Next page is a homework. Homework assignment. I hope you can handle, which is kind of similar to what we did in the previous page. You have now you have a distributed loading. How's that? So distributed loading means, well, you have a linear change of shear. This is a point force 500 Newton applied. What's this? Oh, how do you handle this? This is a cable, right? Cable develop the tension. This is the external force, but first of all, you have to break it down to 2 components. One is this force. One is that force. Okay? And then, does this matter to you? This one doesn't come into play anyways in your shear and moment diagram. So you're going to completely ignore that when you draw shear and moment diagram. However, knowing that support reaction AX is not to 0, okay, be careful, equal and opposite to this tension's X direction component. So when you draw a free body diagram of the entire thing, don't casually set AX equal to 0 because I've been doing that. But no, in this case, AX is equal to opposite to this component, which is develop the tension in the cable. Okay?
You consider the
Yeah.
top too?
This one?
Yeah.
No, I'm going to cut.
Oh.
Yeah, I'm going to cut. And then this is the tension, because this is a cable. That's much easier. Tension. This is a cut. This is a cut segment of the cable. And then also that means, hey, right here, you're going to develop tension. That's it. Okay. This is, but as a matter of fact, this is two unknowns, but you know the direction of this cable. Okay, so that's tensile. Okay, making sense? So that means you are actually dealing with four unknowns, but AX and then component of this direction of force, you don't care, because it doesn't come into play for your drawing of shear and moment diagram. Okay. I hope you can handle this. It's not bad. Don't worry about it. Next page. Oh, here's another class example. This is, I don't, oh my goodness. Well, anyways, what's this? This is not the beam. Well, it's a beam, kind of, but what's the problem?
It's more different beams.
Wait. This is a pin supported. Well, you can, of course, create a beam with a pin supported, connecting two beams. But what's the problem if you do such a thing? Reactions. This side is completely fixed supported. That means three unknown reactions shows up. This is called cantilever beam. And then, well, I create a cantilever beam, but oh my goodness, it's too short. Let's just pick up another beam, make a pin here, connect up. That's what happens. Then you are engineer, and then you go like, oh my goodness, what did you do? But anyways, you have to analyze. Okay, this is a situation. So what do? You're going to disassemble at the pin, so you come up with the two free body diagrams. Find out all the support reactions here, and also here. Okay, then you go like, oh my goodness, let's do it. So member AB. So this is member AB. So remember, AB is going to be, first of all, left-hand side is fixed support, so you cannot avoid it, but you're going to come up with a three unknown: shear, reaction A, normal force reaction at A, NA. And then reaction moment, support reaction moment, MA. Keep in mind, I'm going to strictly following the sign convention, okay? Let's just do that. And external for 700 pounds applied here. Here's the B. Then, okay, well, this is a pin, so you have two unknowns. Reaction in X, it's BX. Reaction in Y, that's BY. Okay, the reason why I'm choosing negative and this way is I'm trying to sort of follow through still the sign convention. Okay, that's what it is. And member BC. Member BC is the rest of the members. Once again, I disassemble this member at pin B. As I do that, I'm going to introduce unknown reaction. This is Bx. Now keep that in mind, equal and opposite. That means if you assemble at the pin B, those two forces cancel each other. This is By. Once again, equal and opposite. So if you assemble at the pin B, those four forces all cancel each other. So effectively speaking, this is not the four unknowns. It's only two unknowns. Okay. And right here, you have unknown support reaction Cy. Don't forget external moment applied here. This is 800 pound-foot. There we go. So this is a free body diagram of two bodies, completely disassembled. Actually, don't forget the distributed loading. Okay. So you have a uniform distributed loading, 150 pound-foot. It's just resolved into resultant. So this is a resultant of this distributed uniform loading, which is 150 pounds per foot over 6 foot. So this is 900 pounds. Resultant force. Okay. Now keep that in mind. Suppose if you try to draw a shear moment diagram, do not draw a diagram based on the resultant. Resultant is just simply equivalent. Okay. All right. So based off of these two free body diagrams, you're going to find out support reactions. So this free body diagram, member AB, okay, so this is A, this is B, this is B, this is C. Okay, so member AB. Member AB, I'm going to take, first of all, summation of the moment at location A. Let's just set equal to 0. This is going to give you MA, which is negative. This is internal moment, no, actually support reaction moment, MA is negative, minus.
Wouldn't it be better to start with member BC?
Possibly. Yeah, I'm convinced. Let me just stop right here. I'm going to take a look at member BC first. That could be easier. So member BC, I'm going to take summation of the moment. At the location B, and then I'm going to set equal to 0. Okay. So Cy creates the moment, which is positive. Moment arm is 6 feet. Cy times 6 minus, okay, 800 pound-foot external moment, and minus this 900 pounds resultant force times 3 meters. 900 times 3 meters. 3 foot, sorry. This is equal to 0. So this is going to give you Cy, support reactions. Cy is, looks like 583.333 pounds. Like that. Okay. Next is summation of the force. In y direction, this is the positive. Set equal to 0. This is going to be By plus, now we know Cy. Cy is 583.333 pounds. And then this is the result, negative 900 pounds, set equal to 0. Okay, this is going to give you By. By is now 316.667 pounds. Those are quite important information because now we know this By. Okay. Now Bx, I'm kind of careless because I don't need to know to draw shear and moment diagram anyways. So I'm going to kind of keep it like I'm not going to even, I don't need to know that for a moment. So let's just go back to member AB then, okay? So member AB, well, interestingly, now we know By. So if you take a sum of the moment at location A, this Bx doesn't come into play, Na doesn't come into play. The only thing you are interested in is By. Whoa, that's cool, that's really cool. So this is going to be minus Ma minus By, which is okay. So minus By, which is 316.667 times this distance is, what is it? This distance, 8 plus 4, 12, right? 12 feet. And this 700 pounds applied in here, so this is going to be another negative. Yeah, another negative 700 times 8 foot, right? Set equal to 0. This is going to give you internal, not internal. This is support reaction moment, Ma. Support reaction moment, Ma, is 9,400 pound-foot. Okay. So now I got reaction moment at point A. Then let's just do summation of the force. Y direction. Set equal to 0. So this is the shear reaction at A minus 700 pounds external loading. And another minus, okay, another minus By, which is the support reaction, 316.667, set equal to 0. This is going to give you shear reaction at A, 1,016.667 pounds. Okay, good. Now, I don't know Na, I don't know Bx, but I don't care because it's not going to come into shear and moment diagram. Okay? So now I'm ready to go. So now what I'm going to do, I'm going to assemble at the pin B, construct the entire beam. As I assemble at the point B, Bx, By disappear. Okay? So I'm going to redraw free body diagram and assemblage. This is assembled free body diagram with all the reaction forces known. Okay. So now I'm going to assemble here, and you have support reaction, which we found out 583.333 pounds right here. And then we know shear reaction, which is 1,016.667 pounds. I know moment reaction, which is 9,400 pound-foot. Don't forget your external loading, which is right here, 700 pounds. And then don't forget distributed loading, which is 150 pound per foot. This is distributed loading. And then right here, don't forget externally applied moment, 800 pound-foot. So this is the free body diagram ready to draw for shear and moment. Okay. And Let's do it. I'm really getting tired, but let's do it. Okay, so first of all, shear diagram. Okay.
Didn't you say we needed 20 minutes for the quiz?
Yeah, about 1 more minutes to go. That means I don't think we can draw shear moment diagram. So let me just set the coordinate here, and then let's do it on Monday. Good point. Okay. So I'm going to set, oh yeah, now it's time. Okay. So I'm going to prepare the coordinate for shear moment diagram, and let's just stop here today. Any question? I'm going to continue on Monday. So let's just do a quiz. I'm going to stop recording.